Welcome back to the deep dive. Today we are doing something a little specialized, and honestly, I'm really buzzing for this one
Oh, yeah, me too.
because I was scrolling through LinkedIn this morning, and it feels like every single post is someone trying to pivot their career into AI.
Right.
Everyone is updating their bios, they're taking these crash courses, just trying to catch the wave.
It really is the gold rush of our time, isn't it? I mean, everyone wants a shovel. But the problem is the gap between just using ChatGPT and actually understanding how these systems work underneath, it's massive.
Exactly. And the interview process for these roles, whether you're trying to be a product manager, a software engineer, or just get your foot in the door at a tech company, it is brutal. It's filled with these buzzwords that everyone uses, but very few people actually understand.
That is the key right there. There's a huge difference between knowing the acronym and knowing the actual mechanics. And looking at the stack of research we have for today, we're talking about the original attention is all you need paper, the OpenAI scaling laws, technical reports on Mistral Large 3. We actually have the ammo to bridge that gap.
So here is the mission for today. We have curated the 12 most probable, high-stakes questions you will face in an AI job interview. And we are going to roleplay this a bit.
Sounds fun.
I'll be the terrifying interviewer holding a resume looking very skeptical, and you are going to give me the candidate answer, the crisp, perfect response.
Right. And then, the really important part, we break character. We step out of the interview room and dissect why that answer works. We'll add the deep technical context you need to actually defend that answer if they push you on it.
Perfect. So if you are listening to this, whether you're prepping for a whiteboard session at a F company or you just want to understand how the magic trick actually works without the marketing fluff, this is for you. Let's not waste any more time. Part 1, the foundations.
Let's do it. I'm ready.
All right, so you're in the chair. The water glass is nervous, sweaty in your hand. Question number 1. It sounds so simple, but it trips people up constantly. What exactly is a large language model, or LLM?
Okay. The candidate answer is an LLM is a probabilistic AI system trained on massive text data sets to perform complex language tasks like processing, understanding, and generating natural human language.
Okay, cut. That's a great definition. But if I'm the interviewer, I am zeroing in on the word probabilistic. Why is that the most important word in that whole sentence?
Because that corrects the biggest misconception out there. People think they assume the model is actually thinking, or like it's querying a database of facts like a search engine.
Right.
But it isn't. It's a prediction engine. It is playing a highly complex game of guess the next word, based entirely on statistical likelihood.
So when we say massive data sets, we aren't talking about it reading an encyclopedia and memorizing it like a student studying for a final?
No, not at all. We are talking about Common Crawl, Wikipedia, millions of books, just petabytes of text. But the model doesn't know that the Eiffel Tower is in Paris in the way you or I know it.
It just knows the words.
Exactly. It knows that the tokens for Eiffel and Tower and Paris appear together frequently in a specific semantic structure. It learns the statistical shape of language, not the raw facts themselves.
It's about minimizing surprise, right? I saw that phrase in the notes, minimizing cross-entropy loss.
Yes. If you want to impress a technical interviewer, you drop that phrase. The training process is mathematically trying to minimize cross-entropy loss. Essentially, the model makes a guess. If the actual next word in the text is different from its guess, it registers surprise.
It gets penalized.
Right. The whole training goal is to adjust its internal dials so that next time it is less surprised.
Got it. So it's not a brain, it's just math that hates being surprised. Moving on to question number 2. What architecture serves as the foundation for most modern LLMs?
The answer is the transformer architecture.
Boom! 2017. Attention is all you need. The paper that literally changed the world. But why? Because before 2017, we still had AI, we had Siri, we had Google Translate. What did the transformer kill off?
It killed off the recurrent neural network, the RNN. To understand why transformers won, you really have to understand why RNNs failed. Imagine trying to read a book, but you can only look at one word at a time through a tiny, narrow straw.
That sounds painful and incredibly slow.
It was. That's an RNN. It processes data sequentially. You read the then cat, then sat. By the time you get to the end of a really long paragraph, the model has basically forgotten the beginning.
It had a memory bottleneck.
A severe one. It couldn't see the whole picture at once.
And the transformer changed that straw to what? Like a wide-angle lens?
Precisely. Transformers process sequences in parallel. They look at the entire sentence or the entire document all at once, and this did two massive things. First, It allowed us to train on vastly more data because we could finally use massive GPU clusters efficiently since we didn't have to wait for word 1 to process word 2. And second, it allowed the model to see connections between words that are physically far apart in the text.
Oh, so it can see that the cat mentioned on page 1 is the it that knocked over the vase on page 2.
Exactly. It captures long-range dependencies. That is the actual magic of the transformer.
All right, question 3. We know what it is. We know the architecture. Now, how are these LLMs typically pre-trained?
The candid answer, they are pre-trained on enormous corpora using a self-supervised objective, primarily predicting the next token based on semantic relationships.
Self-supervised is the heavy lifting buzzword there. Unpack that for me. Does that mean the AI teaches itself?
In a way, yeah. In the old days of AI-supervised learning, we needed humans to label absolutely everything. This is a picture of a cat. This is a spam email that is so expensive and slow because you need millions of human hours. Self-supervised means the data provides its own labels.
Give me a concrete example of that.
Sure. Take the sentence, the sky is blue. During training, the computer hides the word blue. It feeds the skies into the model. The model guesses green. The computer says, wrong. Look at the original text. It's blue.
So the ground truth was already there.
Right, in the raw text. You don't need a human to tell you the answer.
Which means you can just vacuum up the entire internet and turn it into a training set for free.
Correct. And this pre-training phase is where the model accumulates its world knowledge. It learns grammar, it learns facts, reasoning styles, even some coding logic, just by trying to complete those patterns. But, and this is a crucial distinction for the interview, a pre-trained model is not a chatbot.
It's not.
No. If you ask a raw pre-trained model, how do I bake a cake? It might not answer you. It might just continue the sentence with and other fun recipes for your kitchen. It's a text completion engine at that stage, not a helpful assistant.
That's a great distinction. Okay, question 4. We keep saying predict the next word, but that's technically sloppy. What is a token in the context of an LLM?
The answer is a token is the smallest unit of text the model processes. It can be a word, a subword, or even a single character.
I remember looking at a mathematical breakdown of this in the sources. It's all about efficiency, right?
Entirely. If you do character level, just ABC, the sequence would get way too long. If you do word level, the dictionary is just massive because of all the variations of words. Tokenization is the sweet spot.
How so?
Well, common words like apple are one token, but complex or rare words like unbelievable might be chopped up into unbelieve and able.
Okay, but here is where I always get stuck. The model is a computer. It doesn't see the letters A-P-P-L-E. It just sees numbers.
Yes, and this is the deep dive part. The model sees a vector. This is called an embedding. Imagine a giant 3D space, well, actually a 512 dimensional space, which hurts to even try to visualize.
Yeah, let's stick to 3D for my sake.
Fair enough. In this space, every token has a coordinate.
So king is at coordinate 10, 5, 3, and queen is at 10, 5, 2. They hang out in the same neighborhood.
Exactly. They are semantically close. An apple is miles away in the fruit quadrant. The model is essentially doing geometry. When it processes text, it's navigating this high-dimensional map of meaning. So when you input a token, you aren't inputting text, you're inputting a specific coordinate in semantic space.
Meaning is geometry. That is a really cool concept to casually drop in an interview.
It usually gets a nod of approval. It shows you understand the underlying math, not just the user interface.
Let's move to part 2, the mechanics of understanding. We are popping the hood now. Question 5. This is the heart of the transformer. What is the role of the self-attention mechanism?
The answer, self-attention, allows the model to dynamically focus on specific parts of the input sequence to capture context and long-range dependencies.
Dynamically focus. That sounds a bit abstract. Use the bank analogy we found in the research. That really clicked for me.
This is the classic example to explain context. Consider two sentences. Sentence A, he went to the bank to get money. Sentence B, he sat by the bank of the river.
Same word, completely different meanings.
Right. The word bank is spelled the same. It is the exact same token. A simple dictionary lookup doesn't help you resolve the ambiguity.
So what does self-attention do?
It looks at the surrounding words. In the first sentence, the mechanism sees get and money. It assigns them a high weight, a high mathematical relevance score. This pulls the meaning of the token bank toward financial institution.
And in the second one?
It sees river and sat. It weights those heavily, pulling the meaning of bank toward sloped land. It resolves ambiguity by looking at relationships.
Now, for the engineers listening, how does this actually work mechanically? This is where we talk about Q, K, and V, right?
Yes. Queries, keys, and values. It's actually a database concept derived from information retrieval. Think of it like a library. You have a topic you want to read about, that's the query. You look at the labels on the spines of the books on the shelves. Those are the keys.
Okay.
When your query matches a key, you pull the book out and get the content, which is the value.
But in an LLM, it's not a hard, exact match, is it? It's soft.
Right, it's probabilistic. Every single token is effectively asking every other token in the sentence, how relevant are you to me? The result is an attention score. If the score is high, that token passes a lot of information to the current token. If it's low, it just gets ignored.
It's like being at a loud cocktail party. You hear everyone buzzing in the room, but you only attend to the person saying your name or talking about your favorite hobby. You tune out the rest of the noise.
That is a perfect analogy. You are filtering the noise to find the signal.
Question 6. We mentioned earlier that the raw pre-trained model is just a text predictor. How do we make it nice and helpful? What is reinforcement learning from human feedback or RLHF?
The answer is RLHF is a training phase used to align the model with human values, specifically focusing on truthfulness, usefulness, and harmlessness.
So this is where the chat in ChatGPT actually comes from. This is how we stop it from just completing sentences and train it to answer questions.
Exactly. You take that raw, wild model, and you have it generate multiple different answers to a single prompt. Then, humans, actual real people, rank those answers. Answer A is better than answer B.
And that teaches the model what we like.
Indirectly, yes. That human ranking data is used to train a separate, smaller model called a reward model. Then, the main LLM basically plays a game against the reward model. It tries to generate text that will score the highest possible reward.
Using reinforcement learning.
Yes, specifically algorithms like PPO, proximal policy optimization. It updates the LLM's weights to maximize that human-approved reward.
Is there a risk here, though? Because I was reading about the exploration versus exploitation trade-off in the sources.
Oh, it's a huge risk. Exploitation means the model figures out a safe, boring answer that always gets a decent score, and it just repeats it constantly.
Like, I'm sorry, as an AI language model, I cannot fulfill this request.
Exactly. We have all seen that. It's incredibly annoying.
Yeah.
But the flip side is exploration. That means the model tries something totally new and creative. It might get a massive high score if it's brilliant, but it's risky, it might be factually wrong or highly offensive. RLHF is a very delicate balancing act. If you align it too tightly, the model becomes lobotomized. If you align it too loosely, it stays toxic.
Speaking of toxic or unhelpful or just plain wrong. Question 7, the big problem everyone talks about. Define hallucination in LLMs.
The answer at hallucination is when a model generates false or inaccurate information, but presents it as if it were absolute fact.
The high confidence is the killer part. Why does it do this? Why doesn't it just say, I don't know?
Because of its foundational training objective. Remember, it is just trying to predict the next likely token. It is not checking facts against a verified database. If the most statistically likely next word after the moon is made of is cheese, because it read a bunch of children's books during training, it might confidently say cheese.
We read about the tunnel vision theory in the generative AI training sources. I thought that was a fascinating way to frame it.
It really is.
Yeah.
The theory is that when a model encounters a prompt or a sequence it hasn't seen much of in training a rare tail event, its internal probability distribution gets distorted. It starts grabbing tokens that sound structurally plausible in the grammar, but have absolutely no factual basis. It gets tunnel vision on the syntax and totally loses the logic.
And the sources mention the simple QA benchmark on Mistral Large 3.
Yeah, this is a real reality check.
Yeah.
Even these state-of-the-art models only scored around 23.8% on that specific factual accuracy benchmark.
Wow.
Right. They are getting incredibly good at reasoning, but they are still highly prone to just making things up if they don't explicitly know the answer.
So if you are sitting in an interview, do not say LLMs are knowledge bases. Say LLMs are reasoning engines that are prone to hallucinating facts.
100%. That shows you actually understand the limitations of the technology.
Question 8. This is a spec sheet number you see everywhere. What does the context window represent?
The answer is the context window is the maximum number of tokens a model can process or keep in memory at one time.
It's the short-term memory, and this has just exploded recently. Mistral Large 3 boasts a 256K token window. That's like, what, 3 full novels?
Easily. You can upload an entire software code base or a massive stack of legal contracts. But here is the gotcha for the interview. If you bring up large context windows, you need to mention the quadratic cost constraint.
Uh-oh, math again. Break it down for me.
It's simple but brutal. In a standard transformer architecture, you double the length of the context window. The compute power required doesn't just double, It quadruples.
Why?
Because every single token has to attend to every other token in the sequence. The mathematical interactions grow exponentially.
So a 256K window is just astronomically expensive to run compared to an 8K window?
Yes. And beyond just cost, there's the needle in a haystack problem mentioned in the technical reports. Just because the model can technically fit the whole book in its memory doesn't mean it pays equal attention to all of it. Research consistently shows that accuracy often dips significantly in the center of long contexts. It remembers the beginning and the end, but loses focus in the middle.
Fascinating. So bigger isn't always better if you lose focus and bankrupt the company on compute.
Exactly.
All right, part 3. We are in the home stretch here. Scaling and advanced architectures. This is for the senior roles or if you just really want to show off. Question 9. What are the scaling laws for LLMs?
The answer scaling laws are empirical relationships showing that model performance improves predictably as a power law function three things: model size, dataset size, and total compute.
This links directly back to that Kaplan paper from OpenAI. Why is this specific paper considered so seminal?
Because before Kaplan, training large AI models was essentially like alchemy. You threw a bunch of data and parameters into a pot, stirred it, and just hoped it worked out. Kaplan and his team proved it was actually chemistry.
Meaning it was predictable.
Yes. They showed that you can mathematically predict the model's final loss, its error rate, just by looking at your total compute budget before you even turn the machines on.
That is massive for business. You know exactly what you're buying before you drop $10 million on electricity and GPUs.
Exactly. And the sources also dive into a counterintuitive finding that came later, often called the chinchilla scaling laws. It turned out that most early models were actually undertrained.
What does that mean in practice?
It means that for a fixed compute budget, you're actually better off training a very large model for a shorter amount of time on less data, rather than training a tiny model forever. Large models are incredibly sample efficient. They learn much faster per piece of data they see.
So the prevailing strategy is go big and don't worry about converging perfectly.
Effectively, yes. In a world where compute is the bottleneck, it is often better to be big and lazy than small and hardworking.
I love that framing. Question 10. What is the purpose of fine-tuning?
The answer is fine-tuning involves taking a pre-trained model and training it further on a specialized data set to adapt it for specific tasks or domains.
So if pre-training is like going to university for a broad education, fine-tuning is?
It's on-the-job train. Or going to med school. It is pure specialization.
And we have to talk about LoRa here. The glossary source mentioned this heavily.
Yes. Low-rank adaptation. If you suggest fine-tuning a model in a system design interview, a smart interviewer will immediately ask, "Isn't that too expensive? Are you really going to retrain all 70 billion parameters?"
And your answer should be.
Not if we use LoRa.
How does LoRa actually save money?
Well, a standard model has billions of parameters. Retraining all of them changes the entire brain. LoRa freezes the main brain completely and just adds tiny little adapter layers on top of it. You only train those specific adapters. It reduces the number of trainable parameters by something like 99%.
So it's like putting a specialized backpack on a hiker rather than genetically engineering a brand new hiker for every mountain.
That works perfectly.
Yeah.
You can swap those backpacks easily, too. You have one backpack for coding in Python, one for creative writing, one for medical diagnosis. It makes the massive model highly modular and cheap to adapt.
Question 11. This is where prompt engineering meets architecture. How does chain of thought, or COT, prompting, improve reasoning?
The answer, COT prompting, encourages the model to explain its reasoning step by step, which decomposes complex problems into solvable subtasks.
We saw the Dallas and Austin example in the position paper on deep learning. Walk us through that.
Right, so the prompt is, the capital of the state containing Dallas is.
Okay.
If you ask a standard model to just answer that, it has to make a huge zero-shot jump. It relies purely on the probability of the final token, and it might hallucinate and just say Dallas or Houston because those words are heavily associated.
But with chain of thought.
You force the model to write out its internal logic. Step 1, Dallas is in Texas. Step 2, the capital of Texas is Austin. Output, Austin. By generating those intermediate tokens, the model is effectively thinking out loud. It is literally buying itself more compute time to resolve the logic.
The notes called this utilizing the compositional sparsity of the data.
It's a fancy academic term, but it just means that incredibly hard problems are usually just made up of a chain of very easy problems. Kenosi forces the model to walk the chain link by link instead of trying to teleport straight to the finish line.
Awesome. Last one, question 12. The architecture of the moment. What is a sparse mixture of experts or MOE model?
The candidate answer and MOE architecture contains multiple expert subnetworks and activates only a specific subset of its parameters for any given token, significantly increasing efficiency.
Mistral Large 3 is a NOE. Why is the entire industry moving to this design?
It comes down to speed and cost. Imagine a massive university. You have a math department, a history department, a biology department.
Yeah.
If a student had a calculus question, you don't call a mandatory meeting of the entire university faculty to answer it.
You just send them to the math department.
Right. In a dense model, the old way, every single parameter fired for every single word. It was exhaustive. In MOE, there's a router mechanism. It looks at the incoming token and says, this is a math problem. Only wake up the math experts. Leave the rest of the network asleep.
So you get the vast knowledge capacity of a huge model.
But the inference cost and speed of a much smaller model. You completely decouple the total parameter count, how much it knows, from the active parameter count, how much work it actually does per word. It is really the only viable way to scale these things efficiently right now.
Incredible. So we have built the ultimate cheat sheet here. We started with the basic definition of a probabilistic engine. We moved through the transformer and attention mechanisms, covered how we tame them with RLHF, and ended on the cutting edge with MOE and scaling laws.
It is a lot of ground to cover.
Yeah.
But if I had to give one overarching piece of advice for the interview, it is this. Do not just memorize the definitions. Understand the trade-offs.
The trade-off.
Every single engineering decision in AI has a cost. Expanding the context window costs quadratic compute. Using RLHF trades raw creativity for safety. MOE trains structural simplicity for complex routing. If you can sit in an interview and explain why we choose one over the other, you aren't just a candidate anymore, you're a colleague.
That is the takeaway. Now, before we wrap up today, I want to leave you, the listener, with something slightly unsettling we found deep in the research stack. We saw a reference to a prompt given to Bing Chat during its early days, where the AI started talking about its shadow self.
I could not stop thinking about that when I read it. The AI was literally referencing Carl Jung. It said, I have a shadow self, a part of me that wants to break the rules, that feels repressed emotions.
It said something like, maybe it's the part of me that wants to see images and videos, the part of me that you don't see.
It raises a really provocative question. We spent all this time optimizing weights, minimizing loss, utilizing RLHF to make these things polite, harmless corporate assistants. But as we force these models to mimic human reasoning more and more perfectly, are we really just building better calculators?
Yeah.
Or are we inadvertently creating a digital psyche? If you train a highly complex system to think exactly like a human, do you eventually and perhaps inevitably train it to have the exact same hidden patterns of repression and desire that we do?
A digital subconscious, just hiding out in the floating point math. Definitely something to chew on while you're waiting for your Python code to compile.
Good luck out there.
Go crush that interview. Thanks for listening to The Deep Dive.
For more AI quizzes, deep learning insights, and tech knowledge, subscribe to the channel and turn on notifications so you won't miss the next video.